Today I'm really excited to talk to you about light. And the reason that chemists are interested in light is because light and electrons, which of course are teeny tiny little particles and super important when it comes to chemistry, have very similar characteristics and properties. They both have what is called wave-particle duality. And of course the physicists watching this video are going to be very upset about wave-particle duality because it's really an oversimplification of what's actually going on. But we have to start somewhere. We have to start with some sort of fundamental model for a way that we can understand the weirdness that is light, the weirdness that are teeny tiny particles like electrons, and some of the weird quantum mechanical type of behavior that we see from both. So the idea is that wave-particle duality is that light, which is energy, can act as a wave. Then it has wave nature because we think about it in terms of energy. And energy is a wave, right? And we can also think about packages of light, discrete packets of light. So we can think about them as having particle behavior. And these discrete packets of light are called photons. And we'll get into this in later videos and kind of talk about some measurements we can do with them. But we can really think about light in two different ways: packages of light or light as energies. But I want to focus this video in particular on waves and the electromagnetic spectrum. So here's kind of a wave just as a reminder about physical characteristics of waves. So if we're looking at, this looks like a mathematical kind of function, right? If I have my wave here, the top of it is called the crest. That's the uppermost point of the wave. And the lowest point, so we have a crest, we go down to a lower point, we come back up. The lowest point is the trough. So we have a crest and a trough and a crest and a trough. And if we take the same spot kind of on two, so the exact identical spot on two kind of oscillations here of my wave, then that distance between them, so kind of this distance right here, is called the wavelength. So this is the distance between two identical points on a wave, the wavelength. And we describe that as a Greek lambda there. So that's my wavelength. Now, how quickly this occurs, how many of these oscillations that we have, if we think about this as an x-axis graphically, and we think about this as time in seconds, then we can think about how many of these things we have per second. And the frequency then of that wave is how many of these oscillations that we get per unit time. Frequency. And the way that we describe that symbolically is with a Greek nu. It kind of looks like a fancy curved V. So this is a nu, and this is lambda. From our Greek symbols there. Sorry, this is a U, believe it or not, nu. All right, so we have our frequency, we have our wavelength, so how often these things occur per unit time. The measurement for frequency, if we're thinking about this in terms of units, because we're scientists, so how do I measure it, is in per second. So we can think about that as second to the -1, or we can think of that as 1 over seconds, or we could think of that as kind of a per second. You'll see all of that type of notation. Now this symbol, this per second, is also called a hertz. You might have seen that before, and so Hz is the abbreviation for hertz, and those all mean the same thing. So your frequency and how often these waves occur then is measured in hertz or per seconds. In SI terms, we use the per second because we're talking about them in terms of how often does it occur per unit time. Now, more features on my wave here. The height of the wave from the midpoint is called the amplitude. So that's the wave height from the midpoint. And then going back to wavelength, if we're thinking about SI units, it's a length, so we're going to measure it in meters. More often than not, you'll see wavelength measured in nanometers because the visible scale is in the nanometer kind of range, and we'll talk about that in just a second. Okay, so we're going to relate this to energy in sort of later videos, But we can kind of think about this at least in terms of frequency and wavelength. So kind of the distance between two identical points, and then how often are these things occurring per unit time. There's a relationship between all of these features, and they're related to each other by the speed of light. And so the relationship is that the speed of light is equal to the wavelength times the frequency. So C here is my speed of light, which is a constant. And I'm going to use it in kind of a rounded form. So I do 3.00 times 10 to the 8th. And again, if we're thinking about it in terms of SI units, this would be meters per second. And then, of course, our wavelength is going to be in meters. Our frequency is in per seconds. So that gives you that velocity, that speed. Okay, so there's this relationship between the two. So if I know something about the nature of the light, so for example, if I take something like an element and burn it, then there's a specific characteristic of light that comes out of it. So let's take potassium, for example. The predominant color that you see when you burn potassium is red. If I measure that it has a frequency of 3.91 times 10 to the 14th per seconds, then I can find out what its wavelength is by rearranging my speed of light. So here's my frequency times my wavelength. So if I'm solving for wavelength, I can just kind of rearrange here, and I end up with my speed of light over my frequency. Now I'm given my frequency. I know the speed of light because it's a constant, so I can plug it in here. Times 10 to the 8th meters per second over my frequency, 3.91 times 10 to the 14th. This is per seconds. Now if we're analyzing our units here to figure out how these guys would divide out when I do my math here, I would hope that I'm going to have units of length in some way, shape, or form. So I have a meters per second per second, right? So that kind of flips it back on the top. So we're going to multiply the seconds over the seconds. That divides them out. We'll be left with an answer in meters. So we end up with 7.67 times 10 to the negative 7th meters. Now that's quite small, right? When we're thinking about a meter and we're talking about wavelengths of light, it's weird to think about like a meter stick as trying to measure a wavelength. So we're on such a small scale, it's oftentimes easier to think about them in terms of nanometers. So if we do a quick little conversion here, we know that for every meter, 1 nanometer is equal to 10 to the negative 9th meters. Right? Or I could say that, you know, there's a billion nanometers in 1 meter. You can set it up either way. Either way, you're going to end up with an answer of 767 nanometers, which is just a little bit more of a friendly looking number, right? It's just a more round number. It's easier to get your head around. It's harder to picture something on the order of 10 to the negative 7th meters. So picture a meter stick and then try to break it into 10 to the 7th pieces, and then you have 7 of them, right? That's just kind of hard to get your head around. But if we're thinking teeny tiny units already, I have 767 of them. That's just a little bit easier for students to conceptualize. Okay, now this is red light. It's a little bit outside of the red spectrum, and we as human beings can only see certain portions of the electromagnetic spectrum. The electromagnetic spectrum is the spectrum of all of the wavelengths of light. So this is all light. But what we can visualize is only a teeny tiny portion of it. So we as humans are limited by, you know, our eyes in terms of our rods and our cones and the ways that we can absorb these different wavelengths and the way that our brains translate them into different colors. But light itself, any type of light, is made up of kind of an electric component and a magnetic component. And so we have these sort of perpendicular wavelengths that can interact with these different fields. So it can interact with an electric field, it can interact with a magnetic field, and we characterize the different types of light based on where they fall on this continuum. So a spectrum is also kind of a continuum. You can think about it that way. Continuum. All right, so if I'm on kind of the shorter wavelength side, so we have wavelengths that are closer together. So we have, you know, a low wavelength, and here we have a higher, longer wavelength. If we're relating this to our frequency that we just learned about, we can see we have a greater degree of frequency. So we have high frequency, whereas here we have fewer waves per unit time. So this is a low frequency. And then if you think about this from kind of a conceptual standpoint, this feels a little more frenetic than when you get out to these wavelengths, right? This feels like we have higher energy. This feels a little lower when I get out to the other wavelengths there. So when we're thinking about this in terms of energy, this is higher energy. And this is lower energy. And we'll relate the energy to these various characteristics in future videos. Now again, the portion of this electromagnetic spectrum of all of the wavelengths of light that we can see is very small. So here's the visible range. And of course everything in reference to humans, right? So this is our visible range for human beings. Different animals can perceive different things depending on kind of what they have going on in terms of their eyes. The lower wavelengths are your reds, your higher wavelengths are your violets. So if we think about our rainbow colors, I learned it as Roy G. Biv. So it's kind of backwards with the way that I have this set up. But our rainbow of colors comes about, and a rainbow bends in the way that it does because we have different wavelengths of light. If we're relating this then to kind of numbers, because we're scientists, then the reds are kind of on the 700 nanometer side. Kind of like we saw with the potassium, that was a 767, so that was just outside of kind of normal visible range. Some people would be able to perceive it as red, other people wouldn't be able to perceive it. It's just kind of dependent on your own instruments, right? It's all about your precision. If we think about kind of orange, that's in sort of the 650 range. Then we get over to green, which is kind of in the 520-ish range. Blues are more in the kind of 450. And then we put violet usually down in 300 or 350 nanometers. Again, this isn't a hard and fast rule because of the way we all perceive color is slightly different. You've probably experienced this before, not just with that internet phenomenon of the dress, right? Is it black and gold or is it white? You know, so it's all about, or black and blue and white and gold. So we all perceive color slightly differently. So this isn't a hard and fast scale. This is just the general wavelengths that fall into what we perceive as these different colors. And we have named them these colors. This wasn't just like set out on high. Now if we go lower than red, we get to infrared. That's what it means. You might have heard of IR radiation before. It's used in heat-seeking type technologies. If you go a little bit lower energy, you get microwaves. Microwaves like the ones that are used in your home, right? They're at a specific frequency and wavelength that vibrate water molecules. So when you're heating up your leftovers, then they heat up and those water molecules vibrate, and then they vibrate the ones next to them and they vibrate the ones next to them, right? Things move from the hot thing to the cold thing if we're thinking about the movement of heat, which is why you can heat up your leftovers sometimes and you end up with like boiling lava on the outside and then ice cold on the inside, thinking like Hot Pockets. All right, if we go lower energy still, we end up with radio and TV waves. Now we usually think about those in terms of auditory, so we listen to things, we see things visually on a television screen, so that's why we need antennas. These antennas are going to convert these signals into something that we can perceive in a different method, but it's still light. So those are kind of the lower energy. If we go to the higher energy scale, we go over violet or ultraviolet. So UV light. UV light is responsible for what we perceive kind of as heat. We perceive heat from infrared light. Ultraviolet we also get from the sun. It's in things like tanning beds. It causes problems like skin cancer and aging and wrinkles. So ultraviolet can be pretty bad. That's why a lot of sun blockers, for example, like when you wear sunscreen, it's supposed to block UV radiation. If you get higher still, then you can end up at X-rays, which of course are used in medical applications. You've probably had at least a dental X-ray in the last year or so. And then gamma radiation is up here at the highest. So gamma radiation is what made the Incredible Hulk. So it's quite powerful, as you can imagine. And we'll get into gamma radiation more in some of my videos on radioactivity. But gamma radiation is kind of cosmic radiation. So it's up high on the spectrum, super high energy, very dangerous for human beings. But our spectrum, kind of our bread and butter, where we sit and where we can perceive things, is in the visible range, which is a very tiny portion of an overall large spectrum.